In this video, what I'd like to do is give you guys another look at the Basel problem from another perspective. And what we're going to do is goof around a bit with divergent series and show you how playing around with these divergent series can sometimes be quite useful. Now, just to make sure everyone's on the same page, the Basel problem is this very famous problem in math, which it asks for the sum of the infinite series given by 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared and so on. And this is a famous result of Euler. It stumped a lot of mathematicians before him, but it was famously proven by Euler in 1735 that this infinite sum converges to pi squared over 6. And this is also very famous for being a very counterintuitive result. After all, if you just take a look at this infinite series, it's not at all obvious that pi should be appearing and where that 6 comes from. But what I'm going to do here is give you a slightly different look using the divergent series, using pretty light machinery. It's going to actually be a very simple argument for why this thing goes to pi squared over 6. And the machinery that we're going to need is quite simple. First, we're going to need Euler's formula, which is e to the ix is equal to cosine x plus I times sine x. Secondly, we're going to need that 1 over 1 minus x can be written out as a power series as 1 plus x squared plus x cubed and so on. That can be seen as a geometric series, and this is just the formula for the sum of a geometric series. Thirdly, we're going to need the integral of cosine x from a to b is sine of b minus sine a. Just a very simple calculus fact. And fourthly, we're going to need that the integral of sine x from a to b is minus cosine b plus cosine a, which is also equal to cosine a minus cosine b. We're going to start with that power series that I mentioned, which is 1 plus x squared plus x cubed, and so on. And I claim that's equal to 1 over 1 minus x. And again, you can view this as a geometric series and the right-hand side as a special case for the sum of a geometric series. The 1 on top comes from the fact that 1 is the first term, and the x is the common ratio. That is, each term is being multiplied by x. And now what we're going to do is we're going to make a little substitution. We're going to say that x is equal to e to the I theta. Now I should point out that this power series representation is only valid for x values such that the magnitude of x is less than 1. And right off the bat, we're going to break the rules here, because e to the ix turns out to have a magnitude of exactly 1. So this is where I immediately begin to goof around with these divergent series. So we're going to break the rules immediately, but let's just see what happens. So what we're going to do is we're going to stick in e to the ix every time we see an x there. So making that substitution, I get 1 plus e to the I theta plus e to the I times 2 theta plus e times I to the 3 theta, and so on. When you square that number, like the 2 or the 3, just goes right up into the exponent, so it's quite simple. And that's equal to, on the right side, 1 over 1 minus e to the I theta. Now let me goof around with this right-hand side a bit. Now what I'm going to do is use Euler's formula. So I have 1 over 1 minus, now I'm going to use Euler's formula here. So I'm going to have 1 minus cosine theta minus I times sine theta. And that minus sign just comes from that minus sign up there. Now what I'm going to do is I'm going to multiply both top and bottom by the conjugate of this complex number down here. Now for this complex number, the real part is 1 minus cosine theta, and the imaginary part is going to be negative sine theta. So that means that the conjugate is going to be 1 minus cosine theta. Now just flip the sign of the imaginary part, so I'm going to have plus I times sine theta. And I'm going to multiply both top and bottom by that. 1 minus cosine theta plus I times sine theta. And on top I get the same thing, 1 minus cosine theta plus I times sine theta. Now on the bottom, what I'm going to get comes from the simple fact that when I take a complex number and multiply by its conjugate, that what is left is going to be the real part squared plus the imaginary part squared. Now the real part of this is 1 minus cosine theta, so I'm going to have 1 minus cosine theta all squared. And now the imaginary part here is minus sine theta, and minus sine theta squared is sine squared theta. Now you could do it the long way using FOIL, but just pointing out that fact that the thing that you're going to get is the real part squared plus the imaginary part squared. Now let me simplify that. So I'm going to leave the top alone. 1 minus cosine theta plus I times sine theta. And in the denominator, I'm going to get 1 minus 2 cosine theta. Just squaring this whole thing out. Then I'll get cosine squared theta. And finally plus sine squared theta. And now I notice that I have the cosine squared theta plus sine squared theta. So that's going to be 1. I'm going to take that 1 and add it to this 1 over here. And I'm going to leave the numerator alone. 1 minus cosine theta plus I times sine theta. And then below I'm going to get 2 minus 2 cosine theta. So very simple. Here I've just moved the stuff up to the top. So now we're going to take this denominator and divide both the real part, the 1 minus cosine theta, and the imaginary part, which is plus sine theta, by the denominator. So I'm going to rewrite this as 1 minus cosine theta divided by, now what I'm going to do is factor out the 2. 2 times quantity 1 minus cosine theta. And then for the imaginary part, I'm going to have plus sine theta over 2 times 1 minus cosine theta times I. And we can immediately notice we get the cancellation here. So we get at the end of the day that the real part of this complex number is going to be 1/2. And then I'm going to leave this thing alone. But I'll just point out that this thing, if you want to play around with some trig identities, this can be written as 1/2 cotangent of theta over 2 times I. But for this video, I'm going to really only concern myself with the real part here. And now, what I'm going to notice is that for the left-hand side, which is a complex number, to be equal to the right-hand side, the real part of the complex number on the left-hand side has to be identical with the real part of this complex number here. So the real part of the left-hand side has to be 1/2, and the imaginary part of the left-hand side is going to be 1/2 cotangent of theta over 2. So I actually get 2 separate equations there. So let me write out that fact that the real part is going to be equal to 1/2. So I'm going to get 1 plus. Now I ask, what is the real part of e to the I theta? And by Euler's formula, the real part is going to be simply cosine theta. And now what is the real part of e to the I 2 theta? That's going to be cosine 2 theta. And what I get here is this infinite series where the theta gets multiplied by ascending coefficients. I get 1, 2, and 3 theta, and so on. And this infinite series will be continued like that. But this is going to be equal to 1/2. Now what I'm going to do, my last maneuver, is I'm going to subtract 1/2 from both sides. I'm going to subtract 1/2 from that side, and I'm going to subtract 1/2 from this 1 here. So I'm going to get 1/2 plus cosine theta plus cosine 2 theta plus cosine 3 theta, and so forth, is equal to 0. So this is a very mysterious formula here, since it's not at all obvious that the left-hand side is convergent. In fact, this is a divergent series, and this thing manages to sum up to 0. Nonetheless, in the theme of exploration, let's continue goofing around with this infinite series a little bit. And what I'm going to do next is make a pretty benign little substitution, which is going to be that theta is equal to x, some new variable x, plus pi. You can think of this substitution as taking each one of these functions and shifting it leftward by some amount. And what we're going to get when we make that substitution is 1/2 plus cosine of x plus pi. And then I'm going to have cosine 2 theta, which is going to give me in the argument 2x plus 2 pi. So cosine 2x plus 2 pi. And then I'll write out one last term, cosine of 3x plus 3 pi plus a bunch of other terms is equal to 0. Now let's make a few observations. Cosine of x plus pi, as I said, you can think of this as shifting the cosine wave to the left by pi units. Now, when you do that, what you'll get is actually the negation of the cosine wave. So you're going to get negative cosine x. And if you draw out the graph, that should be fairly obvious. Now for this one, I have 2x, but I'm adding 2 pi. So I'm going around the circle one complete time, one revolution. So overall, that doesn't change the cosine wave at all. So this is just equal to cosine 2x. And now I have 3x plus 3 pi, which is going to be going around 2 pi, but going around the circle pi radians more. So that result is also going to be negating the cosine wave. So I'm going to get negative cosine 3x. But you can see that the end result here is that for all these cosine waves with odd coefficients, I had 1x there, I have 3x here, the net result of doing this change of variables here is going to flip the sign. Whereas if the cosine wave had an even coefficient in front of x, the sign is preserved as positive. So just to make that pattern clear, I'll write out the next term, which is plus cosine of 4x. And then it'll be negative cosine of 5x, and so on, is equal to 0. And now what I'm going to do is I'm going to negate both sides. So I'm going to get negative 1/2 plus cosine x minus, and then plus cosine 3x minus cosine 4x, and plus dot 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 is still equal to 0. And now what I'm going to do is going to take that negative 1/2 and move it back to the right hand side. So in summary, I get cosine x minus cosine 2x plus cosine 3x minus cosine 4x, and so on, is equal to 1/2. Another very mysterious formula. Since I'll point out one more time that in order for an infinite series to converge, each of these terms has to eventually go to 0 in the limiting sense. But each one of these terms is a cosine wave, and these don't go to 0. So obviously this left-hand side, this series is divergent. But in a weird sense, this thing can be assigned a value of 1/2. I should also point out that if you were to substitute the value x equals 0, you would get the Grandi series on the left-hand side, which is 1 minus 1 plus 1 minus 1, and so forth. And we gave some other arguments in the previous video, that value should be assigned to 1/2. So here's yet another quasi-argument that the Grandy series is indeed equal to 1/2 in some mysterious sense of the word equals. Now, here's where the real magic is going to come in. What I'm going to do next, for my next trick, I'm going to integrate both sides from 0 to y. I'm going to integrate that side, dx, and I integrate the right side from 0 to y, dx. And y is just going to be some other variable here. And we had before that the antiderivative of cosine is sine. So I'm going to have sine of y minus sine of 0, which is going to give me sine of y. And then I'm going to have negative cosine 2x. And when I integrate that, I'm going to get negative sine of 2y. But since I have that 2 in the coefficient, I'm going to have to divide by 2. So you can see the net effect is switch the cosine to a sine and then divide by the coefficient. But keep that sign there. So that means that the integral of positive cosine 3x is going to be positive sine of 3y divided by 3. And a bunch of other terms is equal to. Now on the right hand side, I'm integrating 1/2 from 0 to y, which is easy. That's just y over 2. Now here's the very mysterious part. This formula is completely legitimate. In fact, it's something called a Fourier series. On the left-hand side, what I have is a bunch of sine waves with different frequencies being summed together. And this formula is trying to tell me that this infinite sum of these sine waves is modeling, in some sense, the function y over 2. And let me pause to show you a quick animation of what's going on. And what you're going to see me do is add on more and more terms of this infinite series. And I'd like to quickly show you that we do actually get a modeling of the line. Remember, this equation on the right-hand side is just a line, y over 2. And again, what you're going to see me do in this animation is add on more and more terms of that infinite series containing a bunch of sine waves. And here's what happens when I add on more and more terms, and let's observe what happens. Now you can see that we still get waves, that it's very distinctly waves. But hopefully what you're seeing here is that as I add on more and more terms, and I think I have the first 50 terms summed up here, that these waves are trying to model a line. That is, this middle part just looks like a straight up line. And I claim to you that that line is going to be just a line y equals x over 2. Just the independent variable divided by 2. And to hopefully convince you that this is what's going on, let me take the data cursor and see what we get for the points on this graph. Now if I scroll over to x equals 2, if this line is modeling x over 2, the y value should be 1, at least approximately 1. And we see that that is indeed the case. It's 1.019, which isn't too bad. And if I take some other values, let's say 1.5, we can see that's pretty close to 0.75, which would be the exact value. Let's now return to our calculations. And if you were interested in that sort of thing, this infinite series consisting of trigonometric functions, this whole topic goes by the name Fourier Analysis. And this is an example of a Fourier series, so I would encourage you to study that if you haven't heard of that topic in math already. It's a very fascinating topic of math. And now, what I'm going to do to this infinite series here is I'm going to integrate one more time. I'm going to integrate both sides from 0 to another variable z. So it's going to be integral dy, and I'll do the same thing for the right-hand side. So 0 to z of dy. Now let me calculate the right-hand side first, since that's the easiest. Now I have y over 2. The antiderivative is going to be y squared over 4, but I'm going to have to plug in z So at the end of the day, I get z squared divided by 4. And now for the right-hand side, if I take sine of y, the antiderivative is going to be negative cosine, but I'm going to have to plug in a z and a 0. So I'm going to get negative cosine z plus cosine of 0. And I'm going to write that in a slightly different order. Now cosine 0 is 1, but I'm going to write that first. So I'm going to have 1 minus cosine of z. Just taking the antiderivative. And now, for this second term here, actually let me throw some parentheses around that, just for visualization purposes. I'm going to keep that minus there. And then when I take the integral of this, I'm going to get something similar to this, a 1 minus cosine of something. That's going to be 1 minus cosine of 2 times z. But in the denominator, another 2 is going to come down to join that 2, and I'm going to get 2 squared. That's going to be a second term. The next term is going to be plus 1 minus cosine of 3 times z, and hopefully you're seeing the pattern here, divided by 3 squared. And let me write out one last term. Next one's going to be minus 1 minus cosine of 4z divided by 4 squared. So you can see every time that the coefficient is going to come down to the denominator to make all of the denominators squared. And this is really what's going to get us to the solution of the Basel problem. And of course, this is an infinite series that'll be continued, and that's all equal to z squared over 4. And here we get an infinite series consisting of not of sine waves that we got before, but of cosine waves. And this is, just like the previous case, this is another example of what's called a Fourier series. And now this equation is telling me, or suggesting to me, that this Fourier series is trying to model a parabola, namely the parabola of the form z squared over 4, or I guess you can say x squared over 4. And just like I did before, I'd like to pause for a second to show you a quick animation. And here you're going to see me do exactly what I did last time. I'm going to keep adding on more and more terms of that infinite cosine series. And let's see what happens as I add on more and more terms. And hopefully you're seeing here that on this interval here, that the waves are starting to smoothen themselves out to what I claim is a parabola. And to hopefully convince you that this is a parabola, and more specifically that it's a parabola x squared over 4, let's take the data cursor and let me stick it near x equals 2. Now if this is x squared over 4, 2 squared over 4 is just 4 over 4. So that means that at x equals 2, we should be getting approximately 1. Now when I add on the first 10 terms, I get 0.9901, which isn't too bad. And to give you another point, hopefully you can see that 0, 0 is being modeled accurately. Let me go to x equals 1. So I should get 1 squared over 4, which is 0.25 exactly. Here I'm getting 0.2433, so not too bad. Here's what we have so far with that infinite cosine series that I just showed you. And hopefully you were convinced that this thing tends to model a parabola. And what I'm going to do now, for my next maneuver, we're going to plug in a specific value for z. Namely, z is equal to pi. And let's see what happens here. We have 1 minus cosine of pi minus 1 minus cosine of 2 pi over 2 squared plus 1 minus cosine of 3 pi over 3 squared minus 1 minus cosine 4 pi over 4 squared, and so on. And the right-hand side, just plugging in z equals pi is equal to pi squared over 4. Now let's observe what's going on with these cosines here. What's cosine pi? That's minus 1. So here I have 1 minus minus 1. So I'm going to have 2. Then I'm going to have minus. And now what's 1 minus cosine 2 pi? Well, cosine 2 pi is 1. So I just get 1 minus 1, which is 0, which means this whole term vanishes. Moreover, any term like cosine 2 pi, cosine 4 pi, cosine 6 pi, or whatever is always going to generate a numerator which is 0. You're always going to get 1 minus 1. So these cosines with the even coefficients are going to vanish here. So I claim this cancels, and all the even coefficients are going to cancel. And that's going to leave me with just the odds. So the next one I'm going to write down is this one here, which is going to be 1 minus 1 again. Cosine 3 pi is minus 1. So I'm going to actually get plus 2 over 3 squared. Now this term containing 4 squared is going to vanish. And my next one I claim is going to be 2 over 5 squared, the next odd coefficient there. And then the next one will be 2 over 7 squared, and so forth, is equal to pi squared over 4. Now, if I divide both sides by 2, I can get rid of these 2's here. So I have 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, and so on, is equal to pi squared over 8. And now I've just moved that new result that we just obtained to the top. And this series is interesting in its own right, but the series we're really after is 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on, equals something. Now, notice here that this thing that we're after contains all the numbers, has I could put 1 squared in the denominator. Now we have 2, 3, 4, and so forth. But here we have only the odd numbers there in the denominator. And now, just to give this series a name, I'm going to call it what everyone else calls it, which is zeta of 2. Now, it doesn't matter what this is, just treat it as a variable. But this turns out to be a special case of what's called the Riemann zeta function, evaluated at 2. Now I'm going to do another trick, which is I'm going to divide both sides by 2 squared, for the reason that I'd like to relate this series, zeta of 2, to the result that we've just obtained. So I'm going to divide both sides by 2 squared. Now, let's see what happens here. I have 1 divided by 2 squared. 1 divided by 2 squared there. Now I have 1 over 2 squared times 1 over 2 squared. Now I could write 1 over 2 to the 4th, but I'm going to instead write 4 squared. Since when I have equal exponents, I can also multiply the bases. And likewise, I have 2 squared there, which is going to get multiplied by 3 squared. So the new denominator is going to be 6 squared. Then the next one's going to be 8 squared, and so on, is equal to zeta of 2 over, let me just call that 4. 2 squared is 4. Now notice what's going on here. Here I've got all the evens, the 2, 4, 6, 8, whereas in my result I had all the odds. I had the 1, 3, 5, 7, and so on. Now, if I were to take this series and add it to this series, if I take the evens and I add them to the odds, I just get exactly what I started with. I get everything. Now let me write that symbolically. So what I just said is if I take this series containing the evens which we found was zeta of 2 over 4, this series here, and I add back the series containing all the odds, which we found was equal to pi squared over 8. So if I add on pi squared over 8, what that is equal to is the series with everything, which we called plain old zeta of 2. Now you can see here, the thing we're after is zeta of 2, and this is just a simple algebra task here. So what I'm going to do is going to take this thing, 1/4 times zeta of 2, I'm going to move it on to the other side. So I get that pi squared over 8 is equal to 1 minus 1/4, which is 3/4 times zeta of 2. Now I'm going to multiply both sides by 4/3, just to get the cancellation there. And I find that zeta of 2 is equal to 4/3 times pi squared over 8. And now I cancel out 4, so that leaves 2 down there. And finally, I get the result that zeta of 2 is equal to pi squared over 6, which is exactly what I was looking for. And I think that'll do it for this video. Hopefully you've appreciated the miracle that we've just witnessed of taking a series which is divergent and getting a result which was actually sensible, which actually turns out to be a Fourier series. In fact, we saw 2 Fourier series today. And I encourage you to play around with this topic. Sometimes you can get some pretty miraculous results, even though you're kind of messing around with things which don't obviously make sense. So hopefully you've enjoyed watching, and if you like my content, feel free to subscribe to my channel, like and comment on the video, and thanks again for watching.